So for this question, we're asked to solve for a transfer function g, which is equal to theta 1 on t, and we need to find the settling time, rise time, peak time, and percent overshoot when a step torque is applied. So looking at this rotational system that we've been given, it's going to be a 2 degree of freedom system, and that means we're going to need to draw a free body diagram of what's going on here, where the inertia is, and also what's going on here between the two components in series. So if you're a little confused on that, go back and look at the rotational videos that I produced. So let's start off by drawing the free body diagram of what's happening here. So I'll call it free body diagram 1. I'm going to pull out, it's going to be a really kind of small, thin shaft because there's no inertia associated with it. So what I'm going to do is say that, okay, the torque is applied this way, so I'm going to assume that the whole shaft is going to rotate that direction. So if it's going to rotate in the clockwise direction, that means that both the damper and the spring are going to try and oppose it. So if we start with the spring here, the torque that it's going to apply is going to be equal to K, the spring constant, multiplied by the angle which it's twisted at, which is going to be theta 1 since it's up against a wall. So applying the same kind of thing for the damper, so it's going to try and oppose the motion, and it's going to be equal to D, the constant associated with the damper, multiplied by the speed that this component is rotating at. And because this component is between two other parts that can twist, we're going to need to take the difference. So it's going to be the one that we're kind of focused on, which is theta 1, minus what's happening for the other one, which is theta 2. Okay, and dots because it's looking at the speed, not the position of the shaft. Alright, so that's the first free body diagram done. Now let's go over and do the second one, which is going to be what's going on at this inertia part. So I'm going to draw that in. So this time we have a torque that's going to be applied directly onto the inertia. So we'll draw it like that. And I'm going to assume that the shaft is rotating this direction. So that's going to be J times the angular acceleration, which is theta double dot 2. And then we're going to have the damper attached to the shaft, which is going to try and resist the motion. So it's going to be back the other way. And it's going to be the damper multiplied by the speed, again, that it's rotating at. So this time it's going to be the opposite. So theta dot 2 minus theta dot 1. Alright, so now we just need to go ahead and develop our equations of motion. And the equation that we need to satisfy is that the sum of the torques is equal to J theta double dot. So looking at this one, I'm going to assume that this is the positive direction since that's what everything is going. And we can see that we have no inertia term marked onto this. So obviously the inertia is so small that we're neglecting it, and that's going to mean that the right hand side here is going to 0. So putting in the other stuff, we've got K theta 1 in the positive direction, and we have this in the positive direction as well. So what I'm going to do is expand out the brackets. And now I'm going to try and Laplace transform it. So basically everything that has a dot is going to get an S. And now I'm going to try and factorize it. This is just going to make it a bit easier in a moment when I go to solve it. So taking theta 1 out, I've got ds and I've got k. And then taking theta 2 out, the only thing we have is ds. So that's my first equation. I need to get the second one from looking at this second free body diagram. Again, this is the equation that we need to satisfy. So this time I have two things that are going to appear on the left-hand side. Let's go with this as the positive direction. So we've got t being positive, this is going to be negative. And this time we do have the inertia term, so it's going to go on the right-hand side, and it's drawn in the positive direction according to what I've decided. It doesn't really matter what you pick here as long as you're consistent. Alright, so let's go ahead and put everything with thetas on one side, everything else on the other. That means that the t can stay here, and I'll move this term across. And at the same time, I'm going to expand the brackets. Alright, so now I'm going to Laplace transform it, so t stays the same. And these are going to end up with some dots. And I'm going to try and factorize it again just to make it easier. So I've only got one θ1 term this time. And I have 2 for θ2. Okay, so they're my two equations. So you can either solve these by substituting one equation into the other, or I like to use Cramer's rule with the matrix method. So that's what I'm going to do this time. So for that we need to set up our matrices where we have AX equals B. So the A matrix is going to be all the constants in front of our unknowns. So for this equation we have ds plus k, and this one here is negative ds. Gets multiplied by the two unknowns that we had, which was θ1 and θ2. And on the other side, the B matrix is what's on the other side of the equation, so it's going to be a 0. So now we'll fill it in for the other side. So for θ1, it's going to be negative ds. θ2, we get this. And t is the constant on the other side of the equation. And remember that you can go back and check that you've picked up all of the terms that you needed to. Again, I discussed that in the other rotational videos that I did on the topic. So, the transfer function that we're looking for, we were told in the question, is θ1 divided by t. So, what we need to do is solve for θ1 using Cramer's rule. So, on the top line, we have a determinant, and what we need to do is put in the B matrix into the column corresponding to the variable we want to find. So we want the first variable, so this needs to go into the first column of the A matrix. So 0 and t go here, and we just copy down everything else. Okay, and then on the bottom line, we end up with just the A matrix directly inputted. Squared. Cool. So now we just need to go and solve for these determinants. So it's going to be AD minus BC. This one here is 0. These two is going to be a double negative, so it's going to be TDS. Again, AD minus BC. We get that, and now we just need to expand out the bottom line. At the same time I might bring this down to the bottom, so we get θ1 on t, ds on the top, and the bottom line is that. So what we find for these 2 degree of freedom systems is that whatever falls out in the negative here should cancel with something else in the equation, and we definitely have that. This is going to cancel with this. So let me write that out. And something else I can do is I've got an S on the top line, and everything on the bottom line has at least one S. So I'm going to get some cancelling that's going to occur. So D stays, and then we're going to get rid of one S on each of these terms. Now, if we wanted to, at this point we could substitute in numbers, or alternatively, I'm going to try and make this look like our characteristic equation first, and then I'll give us some numbers to play with. So for a characteristic equation, we need the number in front of our highest power to be a 1. So what we're going to need to do is divide top and bottom lines by dj. Okay. So we're going to get d divided by dj. So that's just going to leave us 1 on j on the top line. And here we're going to get dj divided by dj. So that just leaves us with s squared, which is what we wanted, the one out the front. We're going to get kj divided by dj. So that's just going to leave us with k on d. And this divided by this, the d's are going to cancel. So we get k on j for the last term. Alright, so these are the values that we're going to now work with. So what we want to do is just sub them straight in. So 1 on j is 1 on 4, so that's 0.25. K on d is 36 on 15, and that is equal to 2.4. And k on j, this is k, this is j, that's equal to 9. So now we want to identify the order of our system. So for that we just need to look at the highest power of s that we've got, and that is going to be s squared, so it's 2, which makes it a second order system. So now we can pull out our characteristic equation, and equate it to the general form. So for a second order system, it looks like this. Okay. Zeta is the damping ratio and omega n is the natural frequency. So we should be able to find both of those parameters. I'm going to start with omega n, which is equal to the constant. So omega n squared is equal to 9. So omega n is going to be the square root of 9, which is equal to 3 radians per second. We can then pull this out, so the 2.4 has to be equal to the 2 omega n zeta, since they're the two s parts. So 2.4 has to be equal to 2 omega n zeta. Rearranging and subbing in, we end up with a zeta value of 0.4. So to be able to keep going and now figure out the time response properties, what we need to do is figure out whether we have an undamped, an underdamped, a critically damped, or an overdamped system. Now this here is between 0 and 1, therefore we can say that we have an underdamped system, and that means that we can use all the time response equations relevant to something that is underdamped. These were all presented in the recap video I did if you want to have a look at those. So let's go through and start with the rise time. And the equation that we had for this was in fact that omega n times the rise time is equal to a constant. And this constant is from a table. So I've just popped in the table here. So what we need to do is look up for our damping ratio what the constant is. So we decided that our damping ratio was 0.4. So that corresponds to this row. So the constant, which is equal to omega n times that rise time, is 1.463. So now we can rearrange and substitute in. We just worked out that this was equal to 3. So we end up with a rise time of 0.488 seconds. Alright, so the next thing that I'm going to go for is the settling time. And this one is an approximate equation, so you're never going to get the exact number. And it's equal to 4 on omega n times zeta. So again, we've just worked out both of these parameters. They're what's governing our response. So omega n is equal to 3. Zeta was 0.4. So this comes out to 3.33 seconds approximately. Alright, the next thing I'm going to go for is my percent overshoot. So that's the general form of the equation. We just need to substitute in our damping ratio. I'm sorry, I left out the times 100 to make it a percent rather than a decimal. and this comes out to 25%. So the other property I was asked to find was the peak time, TP, and we have an equation again based on the fact we have a second order underdamped system. So subbing in and solving, this comes to 1.14 seconds. So with MATLAB, we have the power to go through and easily look at what this system will actually respond like. So I've written myself a little code here to go do that. So this is just setting up the different constants that we have for the equation. This is telling it that I want to make a transfer function, and this is actually assigning the equation of the transfer function. And the last bit is the step. So we've been told that we're going to have a step input for the torque. So if you run that and see what the plot actually looks like, this is what we get. So on the x-axis is time, the y-axis is our output, and in this case it's the angle θ1. So if we want to compare the values that we picked out, the first one that we calculated was the rise time. So let's select it. So we get an estimate from the graph here of 0.488 seconds. Oh, and if we go back, that's exactly what we had from the manual calculations as well. So the next thing that we looked at was the settling time. All right, that's this point out here. And we have an estimate of 2.8 seconds. If we look back, we calculated that it should be 3.33. Remember, this is an approximation formula, so as long as you're kind of ballpark, that's as good as it's going to get. Next thing was the percent overshoot. So we can get that from looking at the peak response on this graph. So you can see here we've got an overshoot of 25.4%. Again, that matches what we had here. And we have the peak time. So that's going to also be associated with the peak response. The time here is 1.15 seconds. So that's pretty much what I've got here. So that's all there is for this question, and I will see you in another video.